I'll introduce you. Cool. So Mingwei, thank you so much for joining us today. I first saw some of your work when I went to a LangSec workshop, and I thought it was super cool. And I think I've felt for many years now that language models hold a lot of potential for network protocol analysis. Amusingly, I started thinking about that problem before they were good. Like when we had BERT, and that was all we really had to work with. And now we have these incredible language models that can do all sorts of things. I haven't worked on it at all though since then, so I'm really excited to see some of what you've been working on, and I believe that some of this work is also a collaboration with Sheng Peng, right? Who is a member of our seminar group and comes to events sometimes. So we're really happy to have you here presenting today. Thank you so much for coming, and yeah, the floor is yours.
Oh, thank you so much for the introduction and welcome. So, as mentioned, my name is Mingwei Zheng, and I'm from Purdue University. So today I'm going to give a recent work, a larger model agent for functional bug detection in network protocols. So before we start, let me give a very brief introduction of myself and also my research. So I'm a final year PhD candidate at Purdue CS, advised by Professor Xiangyu Zhang. And my research focuses on the intersection of larger models and software engineering. And I build automated tools to improve the software reliabilities. Including influence those formal specifications like the network protocol input formats from directly the code or from the documentations. And this kind of specifications can actually be used for some downstream applications such as fuzzing and differential testing. And I also do some multi-model auditing to support some bug detection. And the work I'm presenting today is actually belongs to this kind of multimodal auditing for functional bug detection. And currently, I'm still doing some testing for larger model agents, this kind of stuff. But the high-level goal is try to improve the software reliability and trustworthiness. So today, since we have mentioned we are trying to find functional bugs in network protocols, we first need to say, so what is network protocols? I guess the audience here probably already know a lot about this, um, but probably this is to avoid someone who don't have too much context. But network protocols are just the rules that allow different devices to communicate. And they play a very important role in everyday technology, like from secure web browsing to IoT connectivity and also cloud computing. So essentially, network protocols are actually used everywhere. So it is actually very important in our daily life. So network protocol reliability is quite critical. So this is because that this kind of network protocol bugs can actually cause serious consequences, like some service disruption and also some security breaches and even some data loss. So ensuring the reliability of network protocols requires not only low-level safety, which has been studied by many traditional testing works like fuzzing and some static analyzers. But also, there are also some high-level semantic conformance need to be satisfied in order to achieve the overall reliability. However, the high-level semantic conformance to this intended behavior, this part is actually underexplored. So there are some possible reasons behind. This is because network protocols are typically specified in RFCs, which is a natural language documentations, serves as the official standards for these network protocols. And this kind of natural language documentations tries to describe these semantic properties in very long and informal text, which actually makes it hard to connect the specification content directly to the implementation. And also, unlike those memory bugs, like those low-level safety bugs, these semantics violations, or we say functional bugs, sometimes don't directly crash the system, but it still breaks the semantic correctness. So this actually makes these bugs even harder to detect. Let's probably see a functional bug example that our tool discovered in FR Outing's Babel implementation. So Babel is a routing protocol specified in RFC 8966, which requires this specification actually requires that the routers to send a sequence number request if all feasible routes are lost, but there are still some unexpected unfeasible routes remain, as we can see from this part. This is actually a subsection from the RFC documentations. However, the original implementations miss the check for these unfeasible routes. We can see the original code. It has a function call to the find best route with a third parameter to be 1. So the 1 actually means that this is to check feasible feasible routes. And in the fixed code, this is actually pull request we submitted. We added a check for unfeasible paths, which is by setting the third input parameter to be 0. So by adding this kind of check-ins, which this can actually make the implementation conform to the original RFC requirements. Since the original implementation never checked for these unfeasible routes, the routers could stop without recovery. So these functional bugs actually violate the RFC requirements, but do not direct crash the system. So fuzzing sometimes is very hard to find it directly. And for differential analysis, which actually needs to compare multiple different implementations, so this actually requires multiple high quality implementation. At least one of them must be high quality. But sometimes it is not always possible there exist multiple implementations for the same protocol. Even if it exists, both implementation can be wrong for some specific properties. Like for the bug we mentioned earlier, this bug actually exists not only in the FR routing protocol, but also in a Jack Babel reference implementation. So if you do differential analysis, you cannot find this bug. And also, we know formal verification is actually very accurate and really powerful in many situations. But one thing is like it requires formalized and precise properties, which often requires a lot of manual efforts. So these are all the limitations of existing approaches to try to solve this kind of functional bug detection. And these kind of limitations are all probably due to the same root cause. I think here it is a lack of automated oracles. It is like for different input, we want the oracle to give us some automatic response that, okay, so each input should lead to what kind of consequence. So this is what we mean automated oracles. So here the actual problem becomes, how can we automatically obtain these oracles for semantic correctness? So for network protocols, the oracles actually exist. They're just written in RFCs, these kind of natural language documentations. So the natural question becomes, can we directly compare these RFCs with the code directly? So the answer could be yes, because now with the reasoning abilities of modern language models, this is not possible. The key insight here is that language model is actually capable of extract semantic properties from these natural language documentations, which is FCs, and also it is able to compare these extracted semantic properties with some localized code. We can probably see how language model is able to solve the motivation example here. So for this bubble functional bug, as long as we give the extracted property, which is about the checking of the unfeasible routes, and also the relevant code, which is a function named route loss and some other relevant code. So this is actually the localized relevant code to this specific semantic property. And if we give all this information to the language model and ask it to find the functional inconsistencies between the semantic property and the relevant code, the language model is able to say, okay, we found inconsistency here. There's a unfeasible route check. So this actually gave us more confidence that, so if we provide the legend models with specific semantic property and relevant localized code, legend model is actually able to find the potential semantic inconsistency. So currently the key challenge becomes, how can we find the localized code for each semantic property? So this is actually an issue for many legend model based whole code base understanding, because we know that legend model have some context limitations and the whole code base itself is too large, and people may is not able to put the whole code base into the legend model to make it output some correct response. So this is actually the challenge we need to solve for this functional bug detection problem. So to address this challenge, we propose a legend model-based multi-agent framework. As we can see from this picture, it contains two phases. Phase one is actually code semantic indexing, which contains a code indexing agent, which builds a hierarchical semantic indexing of the whole code base. So this is actually very important for locating relevant code for further detection. Then the detection agent takes the properties extracted from the RFC, and then it will also query the hierarchical semantic index generated in phase one, and to retrieve the most relevant code and checks for potential inconsistency. So by using this kind of framework, it can actually let us directly breach the natural language specification with the source code implementation and automatically discover some functional bugs. So let's see how this workflow works for the motivation example. We can see that in phase one, we need to build a hierarchical semantic indexing of the whole code base. And the left part shows the raw repository structure. And under the bubble directory, we can see there are multiple files like raw.c and also message.c. And for each file, there is also different functions. Like for example, the raw.c contains a function for like route loss and also find best route. And also the message.c contains different functions. So this part, the left part is actually a simplified structure of the whole FRR code base. And then after we apply the indexing agent, we will provide a summarization for each part. Like we can see, like for each file, we give a file summarization, which summarize what this file is actually supposed to do. And then also for each function, we include its functional summarizations to specify its functionality. Like for example, the route loss handles those route loss by finding an alternative route or requesting update, and the send update resend actually is used for transmitting a update message. So this kind of index actually tries to preserve the file system hierarchy, but also provide a semantic map between the semantic and also to the code itself. So this is actually provide a basic for localize the exact code relevant to each RFC properties. So then in the second phase, the detection agent is tries to find the inconsistencies between this the code and its RFC specification. As we mentioned, the first step is to try to localize relevant code relevant to this specific property. As we can see here in the step one, localization stage, the detection agent tries to identify the most relevant functions relevant according to the given RFC subsection, and also the hierarchical summarization we got from the phase 1. And here in this example, it answers that the route loss is the most relevant function to this given property, because this function actually serves for handling route loss. And then the detection agent will try to use this definition of route loss to see whether there is any inconsistency or not. And here the larger model actually gives us the response that, okay, no, currently we cannot give a concrete conclusion, because we still need more context information, like the definition of the find best route and send after resend. So this means that the initial context we got from the first step localization is not enough. We need some additional retrieval to get more context in the following steps. So here, the agent tries to expand the context by retrieving those relevant functions. So here, it tries to retrieve the callee functions of the route of this route loss function. And here, with this broader context, including not only the route loss, but also the callee functions, such as the find best route and the send update resend, the larger model answered that, okay, here we found a functional bug, which is a missing check for this unexpelled unfeasible routes in this route loss function. And then finally, we asked language model to do a self-reflection to revalidate whether and confirm whether this functional bug is correct or it is a false positive. So we can see that, so this actually shows how this kind of LLM-based agent designs help us to locate this functional bug. Okay, so by showing this example, we are able to come up with a design for for functional bug detection. So in the phase 1, as we mentioned in example, we do the code semantic indexing. Here we actually build a hierarchical semantic index of the entire code base. We start from the function level, where each function will be gets a semantic summary. We try to prompt larger models by giving the function definitions and ask language model to return a summary for this function. And then after we generate the function level summarizations, we will use these summarizations, group them together to generate a file level summary. This is also by prompting language model again. And then by grouping these file level summaries, we're able to get directory level summaries, and then finally to reach a repo level summaries. So this is actually a bottom-up based summarization. This process actually mirrors the file system structure, but it gives us both fine-grained and high-level views of the whole code base. So very important is like this indexing is actually a one-time cost. So this means like if you want to use this code base to check with different RFC versions, because we know that RFC versions are RFCs are keep evolving. Sometimes they may update different features for the same protocol. So there would be different RFC versions relevant to the same protocol. And then, but however, this kind of semantic indexing only need to do once in order to check with different RFC versions. But if the code itself is evolving, for example, the developers may just try to fix some bugs or if already implement some new features, then you can just do some incremental updates to these hierarchical summarizations. So in the second phase, we perform this retrieval guided detection. We first begin with localization, which is given the RFC requirements, the agent needs to identify the most relevant functions inside the code. And after stage 1 localization, it will go to stage 2 to try to compare this retrieved context with the RFC requirements. In most cases, it will find the current context is not enough to make a decision. Then it will try to retrieve more context using some provided tools. So for example, we provided tools like query name, which can help to query some struct definition and also some type definition and even some macro definitions. And also query callee and caller, which is to get the caller and callee definitions, function definitions. Because the callee definitions is very important because it is directly inside the context of the given function call. But then for the caller function, this actually decides the calling context of this function. In many cases, it determines the preconditions of calling these functions, which is actually very important in this kind of functional bug detection, because for many properties, it requires like in what kind of situations, which is actually the preconditions, then the protocols should do blah, 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 those kind of actions. So this query caller is actually very important to get this caller context in order to check this kind of preconditions. So once we call this kind of tool use, the definitions returned by these tools will be also returned to the detect stage in order to further compare this retrieved context with the RFC requirements. Once it found it is able to make a decision, it will either report a bug or mention there's no bug detected. If there is any bug detected, then it will go to the validation stage for further self-reflection. So this is actually to check whether the reported bugs are true bugs or false positives. Because in this stage, we gave the whole reasoning steps of the first stage 1, stage 2, and stage 3, and then to let language model to recheck these reasoning steps again to see if there is any mistakes made in the prior stages. These are actually the basic workflow for the phase 2. So our system is actually built on top of AutoGen. If anyone is familiar with it, it is a LLM-based multi-agent framework. And here we use a class 3.5 with a temperature setting of 0.0 for more consistent results. And also we use Traciter for code parsing and retrieval. And currently for evaluation, we already test our tool across 6 different protocols, including not only Bubble and also BFD and some other protocols. And we currently, in these 6 protocols, we already found 47 functional bugs with 40 new bugs, and 20 has already been confirmed or fixed by the developers. We also achieved a very good precision, which is 81.9% of precision, and with an average token cost of only around $5 per protocol. And these $5 actually include 2 phases. The first is the hierarchical semantic indexing, and also the second one is for detection. We also try to do a ablation study to see whether each part of our design really contribute to the final result. So currently we did 3 ablation studies. The first ablation study is like we disable the code semantic indexing. So here it's not like we directly remove the whole phase 1, because then it is hard to give language model any hints for finding relevant functions. And what we did is more like we gave the whole file structures, including the files, the function signatures. But here, what we remove is just the summarization steps. It's like for each function, we only gave the function signatures, including its function name and also its input parameters. Oh, and here we also give the return types to let the larger models to decide so which functions are actually more relevant to to the given semantic properties. And by disable this kind of semantic summarizations, the precision actually decreased from 81 9 to 80 to 51.4, and also the bug number have a large decrease. And also for the second ablation study, we tries to disable the retrieval part. If you remember that here we have a stage 3, which is additional retrieval. So we would like to see if we only have the stage 1, stage 3, and stage 2 and stage 4, which is like we use the initialized context and also the self-reflection, whether what kind of result we can get. So here it shows like the precision and the bug was also got decreased. So this means that this kind of additional context retrieval stage is also very important for this functional bug detection, not only precision, but also the bug findings. The third is the last one, ablation study, which is to see whether self-critics is beneficial to the final result. This actually is related to the stage 4, the validation stage. So as we know, larger models are always suffering from hallucinations, and which have been studied by many different prior works. They try to say how to decrease the or mitigate this kind of LLM hallucinations, and they found the self-reflection is actually very beneficial to lower down this kind of LLM hallucination. So our result also shows like by adding this kind of self-reflection, the precision actually get a very good increase. Like if without this one, the precision is only around 35 or 36, but then by adding this kind of critics, the precision becomes much higher. So we also did some other baseline comparisons with like the GitHub Copilot using different API settings. And if you are interested in those evaluation results, you are welcome to read our paper for more detailed information. So here I would like to make a summary of our contributions. So currently, we think we are the first to consider using large model to do functional bug detection, which tries to target these high-level semantic correctness instead of owning those low-level safety bugs, because those have already been addressed quite well by existing and traditional works. And then we try to bridge the gap between the documentation and the code. This is by aligning the RFC specified behaviors with the implementation logic. We also provide a very novel multi-agent design. So this is so here as we mentioned, we have introduced two different agents. The first agent is a code semantic indexing agent, which builds hierarchical summaries for support more efficient localization. And the second one is a retrieval guided detection agent, which tries to incrementally gather relevant context and to detect semantic violations with high precision. So, although our findings and also our evaluation results already shown that our tool currently is quite powerful and shows the promise of using this kind of LLM-based agents to find any potential semantic violations. But there are still some future directions we would like to explore and try to see how to improve this technique. The first one is like we would like to see how this kind of technology can be expanded to the other domains. Because as we have seen from the overflow, the method itself is actually general. It can apply to any domain as long as this domain have very high quality documentations. It could not be RFCs because we use RFCs because that We know that network protocols have very good documentations, which is RFCs, which actually acts as the official specification standards for network protocol implementations. But there's also some other domains, probably those kind of, those codecs, probably they also have very high quality documentations. So we would like to see how the current tool itself can be directly applied to these domains with high quality documents. But then another open challenge is how to adapt this tool when the documentation itself is incomplete or with low quality. This is actually an open question that currently I have no direct answer to that. But what I am thinking about is like, so probably we can let the large model to infer the intent of the developers by either understanding the comments of the functions or probably using those incomplete documentations. It is just try to gather different information source and then to see whether it can try to infer a more accurate developer intent. The second future direction is like we would like to improve the retrieval strategy, probably by using some embedding-based similarity search. So we know that this kind of embedding-based search can probably help us to quickly shortlist those candidate functions in order to improve the retrieval performance. And another thing is about also about the validation strategy. So this is a part I would like to say. So this is also a question we are always trying to ask ourselves. So when we are trying to, we sometimes find some bugs by this kind of static tools, and then try to write either a pull request or an issue to the developers to let them confirm whether this is bug or not. Well, multiple developers asked us the similar question. It is like, can you confirm this is a real bug by giving us some kind of POC? But since we are using static tools, we're actually not able to generate a POC directly by our tool. So, but the situation is like the developers sometimes also have it's very hard for the developers to confirm this is bug or not without this POC information and those kind of dynamic execution information. So if we are able to integrate this kind of POC generation to this kind of static bug detection technique, this could further increase the confidence in these detected bugs and help the developers to maintain and also fix these potential issues. So this is actually what we did recently, and we are very happy to share in this seminar, I think. And as we mentioned, we try to introduce a larger model-based agent to detect functional bugs in network protocols by including two different agents. One is indexing agent and also detection-based agent. And now we already publish our paper in arXiv, and also we have open sourced a prototype implementation in the GitHub. So if anyone is interested in our paper or interested in playing our code, you are welcome to use this QR code to get this information. And another thing is like currently we are so in my prior PhD years, I also did some other research tries to do network protocol testing, including some static analysis techniques to extract the input formats directly from the network protocol parsing, so that this kind of inputs can serve as some basics to support fuzzing and improve the coverage. And we also use this kind of inputs to do differential testing in order to find some find some violations in the protocol parsing implementations. And we have some other relevant research of using large models to compare documentations and the implementations. So if you are interested in these works, you are welcome to visit my homepage and take a look at these papers. And if you have any questions or if you want to have some future collaborations, you can always contact me through my Purdue email. Yeah, thanks. So yeah, this is all for my today's presentation. Let's go to the Q&A section.
Mingwei, that was great. Thank you so
Mhm.
much.
Thanks.
Um, Maybe I'll just start us out, and then I'm sure other people will have questions.
Mm-hmm.
So
Yeah.
something I've encountered, which you kind of referenced, is not very good specifications, right? Like the RFC has mistakes or omissions, and I think it's even worse or much worse, like in industry than it is, in RFCs, right? Like a lot of
Yeah.
times docs in industry are not updated for very long amounts of time.
Yeah.
Have you thought about maybe going like the the opposite problem of determining when the documentation might be out of date or something, like for example, by leveraging Git information and having a language model look at the track changes or that type of thing?
Yeah, I think this is actually very good questions. Sometimes it is like the documentation itself is out of date because sometimes the developers sometimes they don't have time to update their documentations, or even sometimes like in the network protocol domain, sometimes there is some intentional implementation choices made by the developers. So this can lead to some um, probably lead to some inconsistency between the actual implementation with these RFC documentations. So sometimes, so this actually means like if there's any consistencies, this is not only bugs or potential violations inside the code, but also the documentation itself needs to be updated accordingly. So so yeah, I think this is a very good opportunity here. It is like when we are trying to find, if we find any inconsistencies, we also try to confirm like if this is a true bug of the implementation, or say if we say, okay, so it is actually documentation is not enough or not correct. So I think this is actually we can do this in the detection or the validation step because once the larger model make a decision, we still need human involved here to make a decision like whether this is true bug or not. And this part, we should not only say it is true bug or false positive, but also we should have another another thing is like, so we need to see whether this is actually a mistake or an out of state documentation reason. So I think this is actually a very good suggestion. And also one thing I would like to say is like, actually, I would really like to see if we can have this kind of spec and code evolution. This is actually probably very helpful in the future, like LLM based software development. Yeah, so I think this is actually very good suggestions. I think in the LangSec workshop, I think in that workshop paper, I actually mentioned that we found sometimes it is the FC descriptions itself is not quite clear and it can be improved by add some more detailed constraints in the FC descriptions so that the developers can understand the actual semantic requirements more better so that to help to lower down the chance for writing some bugs. Yes.
I guess one question, great
Mm-hmm.
talk. One question I had was related to your validation. So you were mentioning that
Mm-hmm.
uh, you have an agent that does self-criticism, right? And then, uh, so then it produces bugs, and then you have to manually look at them and make sure that they are functionally valid, right? But Yeah, go ahead. Sorry.
Yeah, sorry. So here the stage 4 validation, it is like it has additional LLM agent to try to check the reported bugs and also the reasoning process to check whether it is true bug or not. So in this phase 2, currently we don't have we don't ask human to involve in this retrieval guided detection. It is only once it finishes all this bug reporting, like for all the true bugs reported generated after the done stage, we will have humans to do the evaluation and then to see whether these bugs are true bug or false positive. So in stage 4, we don't have human to do this kind of additional validation.
Yeah. I guess that what I was asking was this labeling of true positive and false positive. Is that done by a human, or is that what stage 4 is for?
This is done in the stage 4 by large model agent, not by.
Okay.
Yeah.
Okay. And another question I had was that when you're making these PRs and reporting them to developers, have you seen any pushback, or how open have they been to your methodology?
So you mean that when we use this kind of tools to detect the if we find some bugs and we reopen some issues or pull requests, how open those developers like how they accept these bugs? Yeah. I think it is actually probably determined by projects. Like in the FR project, I think they are quite open to these bugs if we can give them very good explanations, and also if we are able to give them possible fix. They're really friendly and would like to try to merge these bug fixes into their code bases. But yeah, we also have some other situations that when developers said, okay, so we're not sure whether this is true bug or not. We have this kind of situations in another open source repository. I think it is MS Quick. It is like the developers mentioned, okay, so this is a potential issue, but we need more time and more efforts to determine whether this is bug or not. But the thing is, like, they still mark it as a potential bug, a charge bug. So it means like they still consider this might be an issue, and they want to put some other efforts and some additional time to diagnose and confirm whether this is bug or not. So I feel like currently we feel like the developers are quite friendly in this bug confirming process. But the only thing is like since this functional bug sometimes is very hard for them to determine, they would like us to see if we can provide the real test cases like the POC or even some symbolic test cases. They are more than happy because this can actually help them to further diagnose and confirm or even fix itself.
Yeah, I totally agree. And definitely, like some of these functional bugs, all the situations have to be perfect for you to be able to reproduce it. So it might actually be pretty difficult to come up with a good POC that can trigger the bug.
Yeah.
So using these, like the future work that you outlined to use an LLM to get there would be definitely very useful. And I had another suggestion or a thought that came while you were giving your talk, which was that I also encountered a lot of these network protocols that do not have a specification, where their whole approach is that the code is the specification. So, and there are different implementations that are all supposed to agree as well in different programming languages. So I was also wondering if uh, the first agent that you had, which was the code semantic indexing, so could that actually be used to generate the RFC in the first place from the code? If you think that the code is the gold standard specification for some definition of that.
I think this is actually a very good suggestion that I haven't think about it before. But I think because for function level summarizations, it is and to file level summarizations, For each file, if it is, if the repository is maintained in a structured way, each file should include functions which are actually belongs to very similar functionalities, like for routing and also for problem message. This kind of so this actually, I think this kind of summarizations can actually serve and aggregate it together, and then we can, I think the way is like we can probably modify the way we do summarization, because we see currently the summarization itself is more like a very high level summarization of the property. Like this function is served as like route loss, and then try to recover some potential route. But if we want to recover a better RFC, then we probably need more detailed information, like even it's how this function is actually used for route loss. Like for example, it is by first checking feasible routes and then check unfeasible routes. I think here what we need to update our tool is like we need to make this kind of summarizations more detailed, and so that we are able to get more useful information and actually more actionable information for generating this kind of C documentations. But I think this is a potential way to do that, because once you get these function level summarizations, we can also get the file level summarizations. The file level summarizations, in most cases, it should be relevant to a specific module, like we say parsing part. And then probably the summarizations of this file level summarizations can be directly used as the RFC section for the message format section. So I think this is actually a possible way to do that. Yeah.
Yeah, thank you. And yes, I agree that it is a possible way to both generate a specification as well as make some minor fixes in an existing specification where things might not have been clear, as you also alluded to earlier.
Yeah, and also I think if like for protocols which does not have RFCs, yeah, you can also probably use different implementation. As you mentioned, if the protocol have implementations using different programming languages, then you can first use these different implementations with different programming languages to do a kind of comparison. You can probably build a semantic indexing of both implementation and try to probably use a graph to connect the two semantic indexing together, and then see if there is any inconsistencies inside, and then first try to probably here you need some human to decide which part is correct or not, and then try to solve any inconsistency before you generate a final RFC documentation. Yeah.
Mingwei, how do you think work like this translates into bug discovery techniques for totally arbitrary software not related to network protocols? Like if I work at Microsoft and I work on Microsoft Word and I say, Mingwei, I want to hire you to help us find bugs in Microsoft Word, right? Totally different domain. To what extent will these techniques scale over?
Yeah, actually, this is actually quite interesting work. This is also relevant to the internship I did in Microsoft.
Yeah.
I also use this tool to find bugs in Microsoft products. So actually, I think the current thing is like if so for many products, they already have different kind of documentations, and some of them are very high quality documentations like the RFC, so that I can directly use this documentation to find bugs. But there are also situations that the RFC itself is not complete. Then in this case, what I would like to do is try to use this, but the another thing is like, so for many product code bases, they have very good, let's say, test harness. It is like, although we cannot directly do a comparison between the documentation and the code, but we are able to use those documentation to try to ask language model to infer the intent of some components, and then try to use this to enhance the current test harness, and then try to test the different semantic properties of like different APIs or different components. So this is actually another way of probably using this kind of techniques. Although we are not probably directly using the whole phase, like the two phase, the code semantic indexing and also detection, the retrieval guided detection, but we actually use this kind of semantic code base understanding to guide the testing of the different code bases. Like for example, sometimes when we are generating test cases, we still need some information of some callee and caller functions, and then we are able to use this kind of tool use and then to retrieve some other additional context in order to help us come up with a better test cases in order to enrich the current test harness. So these are all potential applications of this tool, not only to this kind of network protocol based functional bug detection. Yeah.
That's super cool. Yeah, I think a lot of people are starting to realize that we need like a new suite of static analysis tools just for building good context for the language models, right?
Yeah.
In fact, there are whole startups that are working on that problem now. So
yeah, I remember my team, my group member, I remember, so we're from another, we're from the Xiangyu Zhang's lab, and then the postdoc in our group also gave a talk in this seminar. If you remember, it's Chengpeng Wang. So
yeah,
what he's building is also using large model agents to do static analysis to find some, but his focus is more on low level bugs. They are building the rapid audit and try to find low-level safety bugs, including those non-pointed reference and also some memory leak with a compilation-free manner. So it is like it does not require to compile the whole and build the whole repository, but still able to find some violations in a very high precision. So this is
right.
also very relevant works done by my group. Any other questions or suggestions on this work?
Maybe a good thing to end on, Mingwei, would be what are you doing next? Are you going on to do a postdoc somewhere? Are you on the job market? Do you want to be a professor? Are you going to go work at Microsoft and fix every bug in their code base? What's next for Mingwei?
Yeah, so I think for the next, so I think at the end of this month, I'm going to Amazon for another internship.
Cool.
Yeah, I think that team is the Amazon Q developer team. So they are also focused on this kind of large model agents based code understanding and code generation tasks. And then after that, I'll probably start to find a job. Currently, I'm more interested in finding an industry research position. Yeah.
Uh-huh.
Yeah, this is my current focus. I feel like, because I feel like currently during my internship in Microsoft, I feel like I'm really interested in those kind of industry-based research. It is like they provide some real world problem, which because we also have some collaborations with the other production teams, and we found what their real need is, and then they have some problems and say that, okay, here's a problem we have, and then can you come up with any solutions using your domain knowledge and also your
Yeah.
skills and try to help us to solve the problems. And this actually, during this process, I try to use either large model-based techniques or either static analysis-based techniques to help them try to make progress. This actually gave me a lot of, I mean, I become more satisfied with myself, I mean. I feel like what I'm doing is really making some achievements and make some changes in the real world products. But this actually makes me feel very happy. Yeah, so this is actually the reason currently I feel like I'm interested in this kind of industry-based research. But sometimes I also feel like, who knows, in the future, probably one day I also change my mind. And feel like I want to go back to academia again, and then probably have my own team and then have more students, so that we can work together in some more interesting directions, which can lead some directions. So these are all potential directions, I feel like. But currently, I don't know. Yeah, currently I just feel like I will go to industry research at this moment.
Cool. Well, I hope it goes great, and maybe you'll see Daniel Meltzer at Amazon since he's worked on some of those teams before.
Yeah.
I'm actually on that exact team right now. I'm sitting
Oh,
in an office.
so which office are you in?
What?
Which office?
New York?
Oh, New York. I see. I see.
Yeah.
Yeah.
Yes, the Boston Computation Club has is tentacles in every major AI organization, academia, etc. So you may encounter members. Anyway, Mingwei, thank you so much. It was great. They really
You.
enjoyed your talk, and I'm sure more people will watch it afterward and maybe reach out to you with questions. And we really appreciate your time.
Yeah, thank you so much, and welcome to any questions and also even some potential collaborations. Thank you so much. So also thanks all the audience for listening
Okay.
to my talk. Thank you.
Thank you very much.